Welcome to our SIGGRAPH Asia 2022 talk. My name is Meng Zhang. I just started my faculty position as an associate professor in Nanjing University of Science and Technology. In this talk, I will introduce our work, Motion-Guided Deep Dynamic 3D Garments. I co-authored this paper with other two brilliant researchers, Dr. Dugus Lin and Professor Niloy J. Mitra. A great dress can make you remember what is beautiful about life. Dating back to the 1st century AD, an artisan devoted his talent in carving these vivid wrinkled details in marble to depict a man wearing a toga, which was a most characteristic Roma dress during the early centuries. Time goes to 1434, when Jan van Eyck finished his remarkable work, The Arnolfini Wedding. The painter applied his superb painting technique to render the figure's elaborate tagging dress with realistic wrinkles, foldings, and the material texture. This marvelous portrait is reputed to be the first Ranja painting. In our modern time, techniques of 3D avatar modeling are becoming increasingly popular in today's virtual social media. The realistic garment dynamics play an important role to personify the virtual character and bring the digital avatar to life. One mainstream technique to model garment dynamics is physically based simulation. It provides an accurate way to model garment dynamic deformations under the internal and external forces, estimated based on the observation from the real world to mimic the realistic garment dynamics. However, achieving high-quality simulation is difficult and expensive. For example here, with a complex interaction between the garment and the yellow belt, the simulation goes unstable. Hence, there is a growing interest in the parallel approach of learning-based simulation. The garment dynamics are synthesized by the neural network learned based on the observation from the real world and constrained by the real captured or pre-simulated data. Recently, many learning-based approaches have been proposed to model garment dynamics driven using the input character motion. A common learning-based approach is to predict garment deformation at static pose. However, the predicted garment appears stiff and unrealistic across time. Therefore, some researchers extended these setups to the temporal domain while assuming the garment closely follows the underlying body motion and results from its previous dynamic state. A popular recent trend is to model garment deformations by utilizing a skinning-based model. Usually, the skinning weights are fixed and given with a garment template at rest pose. The learning network focuses on predicting the deformation at the canonical pose followed by the skinning. Some works relax a constraint of fixed skinning weights to predict the dynamic skinning weights with respect to the underlying body motion. Solving the collisions between the garment and the body is a challenging problem. Some of the works use post-optimization to resolve the collision after the whole sequence garment prediction, but it's limited to the offline application. Therefore, a mainstream solution is to solve collisions at runtime. A common limitation of all those works is the time and effort consuming when generating the training data. It can even take a few days to generate synthetic training datasets using a physically based simulator, which seriously undermines the advantage of the learning-based approaches. In order to generalize across unseen body shapes, Most methods work with big training datasets consisting of different body shapes and motion sequences. We are grateful for the inspirations from the previous works. In this talk, we will introduce a work of predicting realistic garment dynamics under the motion guidance. We jointly predict the garment deformation and the skinning weights, considering the temporal dynamics, and handle collisions adaptively across frames. Additionally, we train our network in a relatively short motion sequence on a fixed body shape. With the previous history state of the garment and the current body as input, targeting at modeling the current garment deformation, we present a motion-guided 3D garment prediction network to predict the local displacements with respect to the canonical garment state and linear skinning driven by the dynamic blending weights. We set up our training data on a relatively short normal walking sequence. We expect our network can generalize to different arm space settings, different walking style, dancing motions of rumba and salsa on different body shapes, and even a hip hop motion sequence. However, it's challenging to learn a data-driven model that can approximate the large space of body motion and the corresponding garment configurations from a small set of training data. So we need to solve three problems. That is, how to represent garment geometries with low variations, how to regularize dynamic garments in a generative space, and how to enable rollout prediction to capture garment dynamics considering the previous garment states. We assuming the garment closely follows the underlying body motion. Inspired by the existing works, we decompose the garment deformation into the local displacements in the canonical state of the garment, as well as a linear blending skinning that is driven by dynamically changing blending widths to transform the canonical state garment to the post space. The skinning weights are computed based on the Gaussian distance between the garment vertices and the sampled points on the surface. The Gaussian radius is learned during training. More than that, with respect to the underlying body motion, we introduce a body relative garment geometry map. We use a predefined UV map to record the relative position between the garment vertices and a set of seed points sampled on the body surface. Learning such a space from a limited amount of training samples often results in severe overfitting with poor generalization to unseen motion. To overcome this challenge, we learn a compact latent space of garment geometries that act as a generative model for plausible garment deformations. A common practice is to train variational autoencoders to ensure a compact and smooth latent space by enforcing a Gaussian prior on the latent space using a KL divergence score. However, we have only a limited number of training samples. We observe that this does not work well in our setup. Therefore, instead, with a strong assumption that the mean of the latent codes is zero, we enforce latent code variation similar to the variance of the normal distribution. To ensure that any sampled latent code results in a plausible garment deformation, when training the network, we enforce the edge length of the garment geometry decoded from any random sample latent code to be close to that of the canonical garment. Once we learn a latent space of plausible garment deformations, our next goal is to predict the garment deformation at a particular frame by taking into account the underlying body motion and the garment dynamics. We provide the previous garment geometry, the garment velocity and acceleration, and the interaction between the body and the garment. With those maps as input, we train an encoder that can map the previous state of the garment and the body to a latent code in the current frame, which then can be decoded to obtain the garment geometry. We expect the encoder aware the garment dynamics coming from previous dynamic history and underlying body, so we introduce an additional constraint, that is, when both the body and the garment preserve their states, we should obtain the same latent code as in the previous frame. Here we evaluate the effect of no dynamic constraint on a toy model. We observe that this constraint helps to capture more accurate deformations. At test time, given the previous history state of the garment and the current body as input, the dynamic aware encoder maps these inputs to a latent code. Then we decode the latent vector to the local displacements in the canonical state of the garment. Instead of the sparse skeleton joints, we assign our dynamic skinning weights to the body seat points and apply linear blending skinning to transform the predicted garment to the post space. As we train our network on a relatively short motion sequence, we observe that for unseen motion sequences, occasional collisions remain unsolved in the post space. To address this challenge, we optimize for a 2D residual displacement map to resolve such intersections between the garment and the body. And residual displacement is propagated to the subsequent frames implicitly by feeding the final garment as input back to the network. Here we can see our collision handling works well in practice. Next, we show some results to evaluate the generalization of our method. Since we represent the garment geometry relative to the underlying body shapes, our method has plausible generalization ability for unseen body shapes. Here we test our network on new motion sequences of different arm space settings and a different walking style. We further evaluate the generalization capability of our network by testing on challenging dancing motions. We observe that our network trained with a normal walking sequence produces reasonable output for the unseen motion of either salsa dancing or rumba dancing, but also lacks dynamics and suffers from collisions when tested on the hip-hop sequence. Here we train our network for a bodysuit. We test the generalization ability of the network by changing the speed of the motion at test time. Here we test the stability of our network at predicting long motion sequences at test time by iterative rollout prediction for more than 1,000 frames. Our network can utilize its prediction as input in the subsequent frames and produce reasonable predictions for long testing sequences. Here we demonstrate our method on a pleated skirt with highly dynamic deformations. We evaluate the generalization on an unseen catwalking sequence. We compare our method to recent learning-based garment deformation approaches on a dress example. It shows that our method can capture more dynamic deformations. We also make comparisons to test the network on unseen body shapes. Unlike those baseline methods, who include multiple body shapes in the training data to generalize across unseen body shapes within the training distribution, we train on only a fixed body shape. Our method provides a potential extension to handle multi-layer garments. Here we provide initial results by demonstrating our method on a two-layered garment. We first learn a network to predict how the yellow dress deforms given the underlying body motion. We train another network for the purple skirt, treating the yellow dress as an interaction body. We believe it's very promising to further explore this direction. While showing high quality 3D results, our method has limitations we would like to tackle in the future. Firstly, we observe that there remain collisions between the garment and the body when generalizing our method across very different motion types. Given the recent advances in implicit 3D representations, we would like to explore a more holistic approach of enforcing collision-free geometry in both canonical and post spaces during network training and enable generalization ability to unseen motion and body shapes. If we can solve collisions well, this will be especially critical for handling multi-layer garments more effectively. Finally, training from real captured data is an exciting direction which will enable to learn deformation properties of garments from the observations without the need of manually setting material parameters and physically based simulation. By the end of our talk, we would like to thank all the reviewers for their constructive comments, Mixamo for the motion sequences. We also want to show our gratitude to Igor Santesteban and Hugo Berticci for their helping on the comparisons. This work was partially supported by the ERC Smart Geometry Grant, Marie Curie Grant, and gifts from Adobe Research. That's all for this talk. If you want to know more about this work, please visit our webpage. Thank you for your attention and listening.